Welcome to my bpho Computational Challenge 2025 submission. First, an overview of what I did. I created an app to handle presentation challenge solutions. Everything's included in this one app, written using NIM, which is a static type systems language to be fast, Raylib for the graphics library I use, and Python for keeping everything simple that's not needed to be done real time. I then solved all the challenges, implemented a library for 2D optics, and implemented a graph plotting library from scratch, and implemented a scene system so that everything can easily be handled in one thing, and finally wrote a paper. This first slide was rendered using in real time, using my 2D optics library. So, the graph plotting library. These are some things it does. Use binary search for efficiently finding what points to include. I use these style objects to easily customize plots where I have a focus on composition, so structure over inheritance, where objects will have style objects, a graph will have axes and so on and so forth, rather than inheriting from axes, which is also faster. Positions then are also expressed using screen proportion and projected, where every sizable graph is an object that wraps graph, allowing graphs to be independent on screen size. And I have a focus on storing as much as I can that doesn't need to be repeatedly computed in real time for high speed. This is some of my graph code, so you can see my definition of all my different types, what they need, and you can see there's a lot of objects all composed of one another. These are some of my methods, for example, generating ticks on the axes, such that each tick is at a nice round number, and the binary search for efficiently finding the range to include in the graph. Next is a bit of talk about the optical simulation I made. So this was, as you see, doing this first slide and many others. This was really heavily optimized to allow handling all those rays and way more in real time. I actually considered the clock cycles required by each instruction. I found data on this and sometimes had to derive alternative formulas to avoid slow mathematical functions. For example, all my interactions are done without evaluating trigonometric functions, which is more complicated but much more efficient. Then also, I do things like finding intensity of rays after the interactions. These are using Fresnel equations or single slit diffraction interference equations. So light can have an intensity of reflection or diffraction similar to what it would have in real life. I also have to convert wavelengths to RGB. I use CIE 1931 color space to do this, and I wrote more detail on my paper in this, talking also about a mathematical model of color perception. I then project all of this through a view object, allowing zooming and panning or rotating of anything I draw, making it nice and interactive. Then also I use gamma correction for accurate linear blending, where the colours will add when they render on top of each other, similar to what would happen in real life. I then derive a lot of maths for this, and this is all detailed in my paper. Rays then use a linked list, as this was an efficient way to implement it. Here you can see some of my code for the view, for example, making sure the zooming in a simulation happens about where you zoom in with the mouse and projecting things in and out of the view. This is then some of my code for the optical simulation. You can see my definition of many different types, this time using inheritance rather than composition, as it was a simpler way to implement it and more elegant. You can see my code here to generate lenses and for some of the interactions on hits. You can then see my code for the actual maths for the interactions, such as reflection, refraction, and diffraction, and solving a quadratic for the correct route to solve the collisions in the case of the arcs and parabolas. As obviously the ray only collides with the nearest thing. This is more detailed in my paper. Then I have some of my intersection resolving methods and getting tangents required for the maths of the interactions. And now the first challenge, and also one of the later challenges, 12 something or other, where I have a prism here. You can see the zooming out and panning, everything, everything is doable using the view. And you can see, so there's the graph of refractive index versus wavelength on the right, and you can see a demonstration of what the refractive index changing based on wavelength causes, which is obviously as the light enters a prism, it's going to reflect and refract, but when it refracts at a different angle based on wavelength, causing it to split into all these different pretty colours. Next challenge, I have refractive index of water versus frequency. I plot the graph, and on the left here, I have a simulation of light refracting as it enters a kind of block of water. It would be quite hard to achieve a block like this suspended in real life, but you can see the colour changing as it enters the block due to the refraction. Next, I have had to implement regression for the next challenge. So I decided to implement this myself rather than using a library. I had to implement both quadratic and linear regression. Quadratic I'll talk about more later. These equations are derived by assessing the partial derivatives of the variance with respect to each parameter of my function. In the linear case, y equals ax plus b. In the quadratic case, y equals ax squared plus bx plus c. I get the partial derivatives of the variance with respect to each parameter, so a, b or c, or a or b, and then set them all to 0, and then solve a system of linear equations with a linear algebra library. I also implement gradient descent, which is an algorithm using AI to find minimums. It's not very efficient in this case, but it was interesting to do. And this is some of my code for my regression library here, and also getting the determination of my different regressions, and then some of my code using all my libraries to initialize all the things to create the lenses and lens simulations. And now here you can see this challenge where on the left I have a thick lens, so a not ideal thin lens in this case, with light coming from a point source, moving back and forth, and you can see the focal point changing. On the right you can see a plot of regression done over the reciprocal of the distances on each side to fit a line here, and the determination, which is close to 1, showing that it's a good model. Next, I have the law of refraction, where travel time is minimised when it's reflected. Same thing for refraction, with a dynamic model that you can interact with. Then, for the next set of challenges, I had to implement projections, and I really wanted these to run in real time, and I was able to do this by using the GPU and code on the GPU, which is called a shader, to do these projections. This runs per screen pixel, so therefore would have to transform from screen pixel position to what position to sample from the texture. This requires the inverse of any transformation, which doesn't matter for light as it travels the same way both ways. And I created a projection object to handle all of my shader implementation and abstract it quite elegantly so that any variables I'm sending to the shader are projected through my view object. This is my code for my projections and my lens shader, for example, here. And here you can see this in action with reflection in a rotating plane mirror, the image in a biconcave lens where you can see both the real image and the virtual image when I move any pixels within the focus. You can obviously zoom in and interact with this because of the abstraction with the view class, just like all of my other simulations. Then I have reflection in a concave mirror, reflection in a convex mirror, and an anamorphic transform with the mapping to polar coordinates. Then I have elevation angle of single and double rainbows versus frequency, plotted and coloured in using my wavelength to RGB with CIE 1931 colour space, like for all my conversions on the top. And on the bottom I have elevation angle versus incidence, plotted for different wavelengths of rainbows coloured in accordingly. Yet again using a GPU to do additive blending. This is why it goes white as it zooms out, and you can see lines at the minimums. Next I have reflection angle of single and double rainbows versus frequency, and this you can see this in real time. You can see what would happen with light entering a spherical raindrop and refracting, and you can see it can actually make much more in primary and secondary because I've arbitrarily made this light incredibly intense to allow all these many orders to be visible. It's very fun to play with this simulation. Next is rainbow generation. So I was generating images of the rainbow with a per pixel calculation. This is most accurate. Any other method you'd have problems with overlap if you're drawing circles, for example. This, however, requires inverse function, so generating the colour from the position It's very similar to what I was doing with the projections with the shaders. This is not possible analytically due to the combination of transcendental and algebraic functions. So I use quadratic regression as I plot my graph and notice it looks like a quadratic. The inverse of this can be found. I also attempt to use Newton's and second method to solve for the roots of to solve for the inverse of this function. However, these do not work. They don't work well. You can see Newton's and second method implementation here, and my actual implementation of the challenge with these various functions, and using my regression library discussed earlier to do the quadratic regression. Here you can then see an image of the rainbow generated at 4096 pixel resolution, moving up and down based on anti-solar angle and the ground here. You can then see that my regression model on this curve. So you can see in red my regression model, and in coloured in based on the wavelength, the actual function. And you can see I fitted it over 400 to 800 terahertz by generating 1,000 points in this range and using them for regression. And you can see it fits very well inside this range, however it gets worse outside of the range. To show this, I also plotted some negative frequencies. Next, I have deflection angle versus incidence angle in a prism. One of the two prism challenges, the first one was actually all the way in the first slide alongside the refraction index versus wavelength. And you can see this is dynamic, the prism angle is changing, and so is the graph and my optical simulation. Next, I have a simulation of corrective lenses, where I have an eye where the focus point is in front of the retina here, and I have a concave lens here adjusting its radius of curvature, and you can see the focal point being moved here. You can also obviously zoom in this interaction and see that the light gets split more into different colours towards the outside of the lens. Next, this is my favourite extension. I created a spectrometer using a phone camera, cardboard box, razor slit, and CD with the back taken off as a transmissive diffraction grating. I then process the images from this phone camera, looking at a diffraction grating in Python, and I use NumPy to do some of my computations in C, which is faster than Python. I then apply gamma correction and sum my RGB channels to get a rough estimate of light intensity. Note this is inaccurate due to the beta filter in the camera having different absorption based on wavelength for the different RGB channels. Then to calibrate my position in my camera image to wavelength, I use a fluorescent light which has peaks at specific wavelengths and linear regression. Then I create rays of equivalent spectrum and pass them in my simulation through a transmissive diffraction grating, just like I did in my spectrometer. And you can see here the image of my spectrometer and the light being split into its wavelengths, and you can see the ray of light in my simulation being split into its wavelengths, and how similar it looks, which is amazing. And on the left you can then see a plot of intensity versus wavelength. Note this is normalized because I can't get units accurately due to the Bayer filter in the camera. Finally, I have a picture of the code for this. So you can see I use an old phone for this, so I could tape to it my spectrometer, my image after all the processing, and some of my Python and Nim code for creating this. Next, I created a technical paper. It's typeset using LaTeX and built to a PDF, as well as all the slides from the presentation being built to a PDF, so that then I can use ImageMagick CLI to generate images from these PDFs, which my program then displays. And yeah, these are displayed in sequence for the paper and scrolling smoothly by having scroll velocity and acceleration variables, which is quite nice. You can see some of my code for this here, and then you can see how I can view the PDF using the images generated inside my program. Now, this is my paper presenting all the work I've done. Goes into a lot of detail, mainly about my geometric optics simulation and all the maths required for this, as well as some interesting bits like the wavelength to RGB conversion with a potential model of perceived colour, and It has a table I found of the latency and throughput of different instructions. And with that, that is it. Thank you very much.